Hello, everyone. Thank you for joining us this morning. Welcome to the Bifrost for Maya AU workshop. We have a super hands-on session lined up for you today, led by our subject matter expert, Roland Rayer. He's going to walk you through your first steps in visual programming with Bifrost, starting with programming a function that examines whether and where geometries touch and intersect. Before I hand the floor to him, I just want to mention a few quick things. First, if you have a question while he presents, you can do so in the Q&A panel at the bottom of your screen. We'll get to them as quickly as possible. John, who you can also see here, will be in that Q&A panel answering questions, and then Roland will also answer as many of them live as possible. We will be recording this session and posting it on YouTube in a few days as well, so you can always go back and watch it again. So without further ado, I will hand things over to you, Roland.
Hello all together, my name is Roland Rayer. I'm the technical specialist for the Maya side of things here in Germany. You can hear it from my accent. I'm doing this for quite a while, so I know the first Maya version, or seen the first Maya version, being sold. And I worked for quite a while here with Bifrost already to, find examples to learn how everything works and to be able to tell you how it works. John, do you want to introduce yourself?
Yes, I'm John Capleton. I'm Roland's colleague, his counterpart in the UK. So I guess I'm relatively new to Autodesk compared to Roland. So I've been here for a couple of years. So I'll be hopefully answering a few of your questions in the answer box that down there. And if there's anything that pops up that immediately says something, I might stop say, Roland, there's a question coming in, blah 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 blah. Anyway, but enough about me. I'll hand you back to Roland.
Okay, I'm going to start share my screen. This is the second video introducing Bifrost for artists. If you haven't seen the first video yet, you might want to do so, especially if you have no experience with visual programming. In this video, I want to talk about spatial queries in Bifrost. These are functions that help me to find out how close objects are spatially, whether geometries overlap, touch or interpenetrate, or whether an object can be seen from a specific location. Like in the previous video, I start with very simple objects. This makes testing and analysis of the functions much easier. In the end, I can easily exchange these simple geometries. This sphere and this torus will serve me as test objects. Like before, I will create a new Bifrost graph and then one after another drag the objects with the middle mouse button into the graph. I can delete the default input node. First, I want to try the node Raycast Locations. As the name suggests, this function determines where a ray hits a surface. As inputs, the node has an object, that is the geometry where we look for the intersection with the ray. Then a position from which the ray starts. Finally, a direction in which the ray is emitted. This is a vector which, like the position, is also defined by a float 3. I want to do this so that the object is the torus, the points are the vertices of the sphere, and the directions are the respective point normals of the sphere. In the graph, I can easily connect the torus. From the sphere, I have to retrieve the points with getPointPosition. The normals I can retrieve with getPointNormal. These two arrays keep their order, which means the first normal belongs to the first point and so on. This is an important feature for the arrays in Bifrost. I put the two arrays here and here in the node. The result is an array of locations. What are locations? Locations are something different than positions. While a position is a coordinate in space that is uniquely defined by x, y, and z, a location is a place somewhere on a polygon object. The actual coordinates of the location have to be queried first. It is generated by interpolation of the neighboring vertices. We will come back to this later. Right now, I would like to visualize the result of the Raycast node somehow to understand what I can do with it. There are a number of scope nodes for such diagnostic tasks, including a location scope node. The node has inputs for an object. The locations are located on the torus, so I connect it here. The node can also represent arrows, ideal after our Raycast node. Here I connect the points of the sphere. Directions can also be entered, but that would be redundant here because the rays are already defined by the points and the locations. The result of the node location scope is an object which can be put directly into the output node. We get this beautiful visualization of the rays that, starting from the points of the sphere, hit the surface of the torus. It looks like a disco ball when you move it around. Especially when you dive into the inside of the torus, it becomes very pretty. In the node location scope, you can set the appearance of the arrows as well as of the start and end points, but I'm quite happy with the way it is. I noticed that most of the points of the sphere don't bring any result after all, even if they are very close to the surface of the torus. Maybe instead of sending out rays, I would query which is the nearest surface point on the torus. I will look for a node for closest. Oh, there's even more than one. This one, getClosestPoint, returns the next vertex of the torus, and getClosestLocation returns the next location on the surface. This is it. This new node I will now use instead of Raycast Locations in the graph. I don't need the vertex normal of the sphere anymore, I can delete it. This looks different now, but I like it very much. If I move the sphere around, it gives a great effect. The colors of the arrows result from their direction in space. If you look at it that way, you might get the idea that you can use it to find out if the objects interpenetrate each other or which points of the sphere are inside the torus. For all points outside of the torus, the arrows point from the outside to the surface. For points inside the torus, the arrows point to the inside. This information can indeed be interpreted. To do this, we compare the arrows we see here with the surface normal of the torus. If the arrows point in the same direction, the starting point is inside. If the arrows point in opposite directions, the starting point is on the outside. These arrows are already calculated in the node location scope, but they are not available here, so I have to calculate them again. A vector from point A in the direction of point B would be the result of the subtraction B minus A. The tip of the arrow is always the first position in the subtraction, the so-called minuend. We take as the position on the torus, we first have to convert the location into a real position. This is possible with the node sample property. Here's already the point position I want to query, but the data type is wrong. This must be float3. So this is my point B for the subtraction. Point A from the sphere goes here. That would be this vector. Next we need is the normal of the torus. This can also be queried with the node sample property. I simply copy and paste the existing node, Ctrl C and Ctrl V, and enter point normal here. This is the second vector for my comparison. To find out if the two vectors point roughly in the same direction, I will query the angle between the vectors. Fortunately, there is a ready-made function or node for this. It is called dot. This so-called dot product is the cosine of the angle between the two vectors. Oh my, how can we imagine that? I'll show you a diagram of it. These are the two vectors we want to compare. These two are inputs for the node dot. As a result, we get the cosine of the angle between the two vectors. This sounds complicated, but is actually quite simple. If this angle is less than 90 degrees, then the dot product, the cosine of the angle, will be greater than 0. If the angle is greater than 90 degrees, then the dot product is less than 0. You can see this clearly on the curve of the cosine. Beyond 270 degrees, the vectors approach each other again and point in the same direction. So we create a dot node in the graph. The two vectors are the inputs, the arrow from A to B, and the surface normal of the torus. Then I ask if the result is greater than 0. And then I have a Boolean array, which has a 1 for all points of the sphere which are inside the torus. But what do I do with it now? Or rather, what do I want to achieve in the end? I would like to have all those points on the sphere that lie within the torus marked in red. Something like this drawing. This would make it very easy for me to see when objects interpenetrate or intersect. So I would like to make points visible. I can achieve this with the node point scope. In this node I can set the color, size and appearance of the points. I would like to have thick red points and I will set this here. The node point scope expects an object as input. I could connect a polygon object or particles, but a list of XYZ coordinates I can't pass so easily. But there's a node construct points which can transform a list of coordinates into an object. Now I have reached the point that I should use the Boolean array to filter out those points of the sphere that are inside the torus. And that goes like this. In the Boolean array, all elements have a 1 whose corresponding point on the sphere lies inside the torus, according to our calculations. From the node findAllInArray, I get a list of indices where in the Boolean array a 1 is located. I can pass this list of indices to the node getFromArray, which filters the corresponding elements from the list of all sphere points. This list of points is then made an object and the points are displayed. Now I just have to connect the result of the node point scope to the output. And voila, there are the points. I can move the sphere and there are always the thick red dots where the vertices of the sphere are inside the torus. I could imagine that I could use such a function in animation to determine if and where animated objects interpenetrate. But for a simple usage, I should first clean up the graph a bit. I select all nodes except the input and the output node. In the right mouse button menu, I find the function createCompound. I could also just press Ctrl G. This will group all selected nodes together in such a compound node. You can recognize compound nodes by this icon. The connections to the rest of the graph remain. With a double click I can dive into the compound node and see what's inside. Everything is still there. At the top of the graph editor I see a path that helps me to find my way around. I noticed that some of the regular Bifrost nodes are compounds too. With a double click I can even dive into the node point scope, for example, and here are more compound nodes. Double click. Interesting. I can even open the nodes with this icon. But with all of these nodes I get a message here that they are not editable. So I cannot change anything in these compounds. If I want to change such a compound, which is quite possible and wanted, I can select Make Editable in the right mouse button menu for the node. Then this compound node is imported into my graph and I can change the contents. Of course, I can still change my own compound node. For example, I want to change the size of the red dots from the outside so that I can adapt the effect to scenes of different sizes. I connect the input point size from the node point scope to the input node. This channel then appears also on the outside of the compound node. Now I will rename the inputs and outputs and give the node a meaningful name. Okay, now I can save the node as part of my library. Right mouse button, the function is called Publish. You already know this from the first video. And now let's have a look at the application of my new function. Here I have a scene with a dancing character with several obstacles around it. I want to find out when and where the character touches the obstacles and then make appropriate changes. If the obstacles are as simple as here and also the animation is as simple as here, you can use animated snapshots to see where penetration occurs. I use this method to place the obstacles roughly. For the fine-tuning, I will now load my new node into Bifrost and connect the geometries in the scene accordingly. The character is my highlight mesh. The obstacles should become the static mesh, but there's a little problem. If I put all obstacle objects together in the node graph editor, there's only one node, but this output is an array, which means a list of objects. While I can connect the array to my node, the output then becomes an auto loop array, which I cannot connect to the output node. So I will merge this array with the obstacle objects with the node merge geometry into one single object. Done. This way our graph looks very simple. Now I want to see if the penetration detection works. Strange, here we clearly have a penetration. Why don't I see the red dots? The red dots are there, but they are too small. How good that I put the value point size to the outside of my compound, so I can easily change that. This is better now. The penetrations are clearly shown and I can change the scene to fix the problem. I have a YouTube channel. When you search on YouTube for my last name, you will find me immediately. It's full of Maya videos, and I will post this lesson here, building this graph on my YouTube channel as soon as I can. Thank you very much for being with us, for watching and hopefully doing some steps here. And I hope I can see you on the next AU again. John, any final words?
So I was just typing thank you. Right, so thank you, Roland. That was informative. And I'll see if I can post a picture somewhere of that thing. Yeah. Fantastic.
Okay, doc. Thank you very much. We're going to close the session now. Thanks. Bye-bye.
Bye-bye, everyone.